Okay, so before we start, I want to say that there's some real potential for injury with this experiment, so please be careful. You're going to be working with electricity, you're going to be working with water, you're going to be working with hot water, you're going to be working with electrical elements that heat up, so be careful, and if there's anything that scares you, make your lab instructor do it instead. Another thing to be aware of is that the way that we're hooking up the circuit in this experiment is actually a violation of the electrical code, so please don't think that you can wire your house just because you've done this experiment. You can't. Oh my gosh. Taking apart the circuit at the end of the experiment is part of the experiment. If you don't do it, you would lose some marks. They can be significant. So do take things apart, but please remember to unplug the circuit before you start attacking it with the screwdriver. Oh my gosh. Unplug it, then take it apart. The circuit will be checked twice by your lab instructor. So I'll tell you where, but you build the circuit, and before you put the face plates on the electrical sockets, you would bring it over to your instructor. They would check it out to make sure it looks okay electrically. Then you'd go back, put the face plates back on it, bring it back for a second check, just because we want to make sure that no wires got bumped loose when you put the face plates on. And if it looks okay on that second check, then your lab instructor will be the first person to actually plug something in. So if there's fire and smoke, it'll be the lab instructor's fault, not yours. Just make sure that you are not the first person to plug stuff into this. It gets checked twice by the lab instructor, and then they will plug it in for the very first time and test it.
Question 1 is meant to be done as a class exercise, and it's actually not worth any marks. But you want to pay attention to how it's done, because you're going to be doing a whole bunch of calculations just like this later in this experiment, and they will be worth marks. So, question 1 says, assume we have a 500 watt stereo, calculate the energy that it'll use up in 1 hour, and also calculate how much it would cost to use that stereo for 1 hour, assuming that BC Hydro is charging us 6.7 cents per kilowatt hour. And I'll just pause there and mention that kilowatt hour is a unit of energy. It's kind of a weird unit of energy, but it's a unit of energy just like joules are. I'll also note that watts are equal to joules per second. So the unit of power, a watt, is just a measure of how much energy is being transferred. So joules per second, that's how much energy is transferred per second. So the first question is the energy it will use in an hour. So what is that? Well, let's first of all stop thinking of this as watts and think of it as joules per second. So 500 watts equals 500 joules per second, and the question wants to know how many joules do we use up in 1 hour. So it's just a matter of converting from seconds to hours. So to do that, we just multiply by 60 seconds per minute and 60 minutes per hour. And so you can plug this into your calculator now and calculate how many joules this stereo uses in 1 hour. Now, there's another way to calculate energy. So remember that I said kilowatt hours are also a unit of energy. I'm going to do that as well. So this is exactly the same calculation we've just done, except that my final answer is going to be in kilowatt hours instead of joules. So again, we start with 500 watt stereo, and we want to know how much energy it's going to use in an hour. So we want to convert this to kilowatt hours. So first of all, I'll go from watts to kilowatts. So multiply by 1 kilowatt equals 1,000 watts. And then I multiply by 1 hour because I want to go to kilowatt hours. So I can calculate this out. It's just going to be 0.5 kilowatt hours. Now this number here is exactly the same as the number you would have gotten up here, except it's in different units. So 0.5 kilowatt hours equals however many joules you calculated here. It's the same thing. The reason why I've done it this second way is that this actually makes it really easy to do question B. So question B says, how much would it cost to use this stereo for 1 hour if we're being charged 6.7 cents per kilowatt hour? So if I know how much energy we used up in kilowatt hours, I can just multiply by 6.7 cents per kilowatt hour and get my answer. So that's question B. So in this experiment, you're basically wiring up your own electrical socket. You'll be doing that into these two yellow boxes. And then you're going to plug appliances into your electrical sockets and measure how much current gets drawn by those appliances, and then you'll draw conclusions about that. On your desk, you'll have a box of equipment, and if you look in there, you'll see the two electrical sockets that you're going to wire up and their faceplates. You've also got a variety of screwdrivers and needle nose pliers in there, which will be useful to you, and you've got some wires, which I'll talk about in a moment. We're going to measure the current in this circuit via one of two different devices. So in Richmond we have a choice. Either it'll be this what's up meter, in which case you would plug in your electrical socket into the top of this, and then the what's up meter itself gets plugged into a regular electrical socket in the room. Or you have this clamp thing, where when you press this, it opens it up. You're going to hook this onto a wire and measure your current directly that way. I will show you later in the video how to use both of these. Now, the instructions in the manual for how to wire up these two electrical sockets is actually really good. So I'm not going to say too much about how to do this. I'll give you some tips. I will say, however, that you're going to get your electrical socket checked twice by your lab instructor before anybody runs electricity through it. So I'll show you in the video at what stages you stop and you get your lab instructor to check it for you electrically, and then I'll show you how you continue with the experiment. But as I said, what's in the manual for how you actually wire up these two electrical sockets is really quite good. So in your box you've got two wires, and one of those wires has got a plug attached to it. So I call that the plug wire. And these loose wires at the end, what you're going to do is you're going to thread them through into the yellow box, and they'll stick up out the top like so. So I'll show you how that looks in a moment. This other wire is called the continuing wire, and it's basically going to connect the two yellow boxes together. So one end of this will thread into this yellow box from the other side coming up, and then its opposite end will thread into this yellow box. So you'll have one wire that connects these two boxes, the continuing wire, and then the plug wire will be connected via the end of one of these yellow boxes. So it'll come out like so. The last thing I'll mention is that if you look, this may be a little hard to see, at the ends of the yellow boxes there's these little trap doors. So that's where the wires get threaded in. Is you would take, for example, your plug wire, these wires on the end, and you would thread them into one of these trap doors so that the wires are sticking up out of the box. So in the next part of the video I will show you what that looks like. So here's what it looks like when you've got your plug wire added to the yellow box. So here's the plug, and you'll notice that the wire goes into the end of the yellow box through the trap door, and these loose wires are then sticking up out of the box like so. And here's what it looks like when you've added the continuing wire. So you can see that the continuing wire connects these two yellow boxes, and then the ends of the continuing wire are sticking up out of the yellow boxes. The plug wire is also coming out of this yellow box, but it's threaded in through the opposite side of the box. So now I'll show you a little tip for how to attach the wires onto the socket. So you're going to have to hook these three wires onto the socket, onto the screws of it. So what I recommend you do is take your needle nose pliers, and if this hasn't already been done, you bend these wires into a half loop, so just like that. And then you would take that half loop and you hook it onto the screw where that wire is supposed to be attached, like so, and then take your screwdriver and tighten the screw down to clamp that wire in place. Once you've done that, you've got a really solid connection. So that's how you attach all of your wires. Bend it into a little half loop like this, and then hook it over the screw where it's supposed to be attached and tighten the screw down to clamp it in place. So you get things wired to this stage where the outlets are actually hooked onto the continuing wire and the plug wire's ends, and everything is wired up electrically the way it's supposed to, and these outlets are actually screwed down onto the yellow boxes. So the only thing left to do is put on the face plates. But you build it to this stage without the face plates, and then you take it to your lab instructor and have them check it electrically. So that's the first of two checks. If everything looks okay, doesn't look like anything got wired wrong, your lab instructor will send you back to your desk, you put the face plates on, you bring it back for your second check. That's just to make sure that when the face plates went on, you didn't accidentally knock anything loose. If everything looks okay on the second check, then your lab instructor will be the first person to test your circuit. So this is how things will look when you're ready to get your second check done. So all you did was add the face plates and screw them down. So you take it back to your lab instructor, they will check it electrically. If everything looks okay, then your lab instructor will actually plug this outlet that you built into an electrical socket, a real one, and then they'll plug an appliance into one of your sockets and test to make sure that it works. If it does, then your instructor will send you back to your desk and you can continue with the experiment. So I'm going to give you some very mild hints on how to do questions 3, 4, and 5. The reason why is that it's quite common by the time you do this experiment for you to have not taken this stuff in class yet. So question 3 says, in the circuit you've connected, the black wire is hot. That is, it's got a high voltage. What's the function of the white wire and the bare copper wire? So the big hint I'll give you here is that though they mention voltage, this question's all about current. So current means electrons that come out of the wall, through the wires, through your appliance, back out through a different wire, and then back to BC Hydro. So current is little physical bodies moving in and out of your circuit. They need to go in via one path and out via another path. So 2 of the wires that we're talking about have electrons, have current flowing through them. There's also a 3rd wire that is meant to act as a fail-safe. The idea is that if you had a hot wire pop free inside a device and touch the outer casing, that'd be quite dangerous for somebody who then went and touched that appliance. So you have another wire that its job is to pull current that has gone where it's not supposed to go back out to ground so that it can't hurt people who then touch the device. So question 3, you need to think about current rather than voltage. So question 4 asks, why does it not matter which screw we attach the wire to on the outlet receptacle? So for example, if I attached a wire to this screw, both slots on this outlet would still get electricity. And why is that if I only attached the wire to one screw? They point out here that there's a metal plate connecting those 2 screws together. That's the key here. Think about that and you should be able to answer the question. So question 5 is a hypothetical question, and what they're asking is, what would happen if you touched various prongs on a partly exposed plug? Now obviously you should never do that, that can be incredibly dangerous, but they're asking you to think about which ones hypothetically would be dangerous to touch and which ones would be hypothetically safe to touch. And obviously never touch any prong on an exposed plug. So question A is which ones would give you a shock, and question B is which ones would not give you a shock. So there's 3 prongs. There's a tall rectangular one, a short rectangular one, and a round one. And they say which ones would give you a shock, which ones would not give you a shock. It's helpful for question 5 to think about your answers for question 3. So which wires are carrying current, which wires are just there as a fail-safe. So think about that and then answer question 5. So now I'll talk about how we measure current in this circuit. And like I said, there's 2 devices in Richmond we might use, so you'll find out on lab day which one your lab instructor has decided to use. This is the What's Up meter, and the way in which you use this is you would take your plug and you plug it into the top of this meter, like so, and then the What's Up meter itself gets plugged into the power box that's dangling above your lab desk. And once you've done that, there's several modes, so you keep clicking the mode button until you find the one for amperes. There we go, amps. And so once you've got it set up like so, you can plug an appliance into your socket, turn it on, and you'll be able to read directly how much current that appliance is drawing. The other device that potentially your lab instructor might choose to use is this handheld ammeter. There's a little button on the side. You can click that and it opens these jaws. You need to set it to the A symbol for amperes, for current. And the way in which we use this is you take your plug and you plug it into the power box that's dangling above your desk. So you get to plug your outlet directly into the power line. Now you'll notice that over here on your plug wire, you've got 3 wires that are exposed, not totally electrically exposed, but the inner wires are showing. Either the black one or the white one have current running through them, and you need to clip this device over one of them. So either the black or the white one, you clip this device over top of it, you have it turned on, and then again, if you plug an appliance into here and turn it on, you'll be able to read directly how much current is flowing through that appliance. So next you're going to be plugging appliances into your electrical outlet and measuring how much current is drawn through them. We have a class set of appliances, so everybody in the room is going to have to share these. Be polite about that. And these are ones that you're likely to see. So a paint stripper, a toaster, maybe one of two different types of kettles, a light bulb. So you're going to be plugging these in individually into your circuit and also in combinations of 2 or 3 as part of this experiment. The appliances will either be on a spare desk or they'll be on a cart waiting for you. So now you're going to plug an appliance into your circuit, and so you select an appliance, and the first thing you want to do is find its power rating. So that's usually embossed right into the plastic somewhere on the device. So look for that, and then you're going to plug in the appliance and also have your meter turned on, whatever meter you happen to be using, and you turn the device on to its highest setting, so its maximum setting, and you measure how much current it is drawing through the meter. Now, keep in mind that that number on the screen may fluctuate a little bit. If it is, choose the highest number that you see. Also, note that with some things that heat up, like the toaster and the kettle, you may need to let them cool off a little bit before they'll actually give you their maximum reading. So just be aware of that. If it's something that heats up, you may need to let it cool down if the previous group had left it hot. Now, once you've got your data, you're going to calculate the energy used in 1 hour by this appliance and the cost of using this appliance for 1 hour. So this is exactly the same calculation as you did in that question 1, which wasn't worth marks. This time it's worth marks. And you're going to use what you've read off of this device for its power rating. Then you're also going to calculate the predicted current. So for that, you use the equation P equals IV, where V is 120 volts that BC Hydro gives us, and the P is the power rating of your device. And then you calculate what the predicted current is supposed to be. You've also measured that current, so you're going to compare the two numbers, what you predicted for the current and what you actually measured for the current, and you calculate a % difference between them. Then you're going to do that all again for all the rest of the appliances, so for all of them in total, and you make a table in your lab manual of that. And then they ask you to comment about the % differences. So are they less than 5% in every case? And if not, can you suggest any reasons for why there's that discrepancy? So next they have you plug in 2 different appliances, and they specify that one of them should be a low current appliance. So the light bulb's actually the lowest one we have. That's a good one to use. The reason why we choose low current ones is that we don't want to flip the circuit breaker. So you choose at least one low current appliance and another appliance, and you plug them both in at the same time, and you measure the current that they draw together. And then you're going to compare how much current they draw together to how much current they each drew individually, because you have that in your previous chart. Once you've done that, you're going to repeat for a different pair of appliances, and then they ask you to look at the patterns and try to predict quantitatively, so with a number, what would happen if you plugged in 3 appliances at the same time. And then they have you actually test it, where you would plug in 3 different appliances at the same time, low current for some of them, and check whether the current that all 3 of them drew is similar to what you expect based on how much current each individual appliance drew. In question 17, they have a picture of a light bulb and a picture of a toaster, and they actually show you the wires inside the appliances. So you can actually see the wire running through the toaster and through the light bulb. And they tell you redraw those pictures on the circuit diagram below. So down here you've got a diagram of plug, and again you can actually see the wires all the way through, including up to the outlets, and note that the 2 slots in the outlet, the wires do not connect there, so there's a little gap between them there. So they're telling you, take this light bulb and this toaster, redraw it down here, draw them actually plugged in. And then you're supposed to use small arrows to indicate how the current flows through these 2 circuits. So you should draw lots of arrows on here showing how the current moves in the wires and also how it moves in the devices. So make sure you draw arrows in the light bulb and in the toaster that you drew down here. So questions 18 and 19 should be fairly straightforward for you to answer, because they're very much based on what you just learned in the experiment regarding plugging in 2 or more appliances and how much current you expect the circuit to draw. So I won't say too much about how to answer these. You should be well equipped to answer them yourself at this point. Questions 20 and 21 have to do with how much current it takes to blow the circuit breaker in your house. And specifically, they ask if you have these devices, and they give you 4 of them, and they're all plugged in at the same time to the same circuit, are you going to trip your circuit breaker? And question 21 asks, how many light bulbs could you plug in without tripping the circuit breaker? So again, these are fairly straightforward. You should be well equipped to answer these.